use that disconnection in practice. You might not use it, but as a synthetic chemist, you always, always, always think about that disconnection. Okay. So we would need a difluorinated enolate. We would need some type of an electrophile. It can be an SN1 reaction, SN2 reaction, who knows? You'd have to eventually attach some type of leaving group to that position. That's the disconnection we think about. And so in order to make this type of a difluoroenolate, one might try to do a deprotonation. And the precursor for that deprotonation might look something like this. You might have a difluoromethyl group. We want to deprotonate this position to get to that type of a substructure instead of this internal position. Okay. However, when you attempt to do that deprotonation, either with strong bases or with weaker bases, you deprotonate. You deprotonate the internal position. You deprotonate one of these two CH bonds there, and not the terminal position. Why? Explain that to me. Hint: it's in the conformational control section. So we're talking about conformational control somehow. But that's the problem. Why don't we deprotonate at this position? Why do we deprotonate there? Okay, so you kind of have a few minutes to brainstorm that phys-org question. We'll be done with this one about 11:15. So I'll give you guys maybe 5 or 6 minutes, and then I'll talk through it with the other slides that I have prepared. Okay? Cool. Got it figured out yet? Okay, we got this puzzle figured out? So let's think about deprotonation of a carbonyl to start. It's easy to draw on paper. It's more complex in reality. Okay, the C alpha position, it's acidic, right? We all had to look at the Evans pKa table, or we have it posted at our hood or at our desk, saved on our computer. Why is the C alpha position acidic in a normal carbonyl? Don't worry about the fluorinated things. Just let's focus about a normal carbonyl. So what makes it acidic? We can draw the arrows in, but when we have a CO bond, so this would be the CO pi bond, right? And maybe the two substituents, one's coming at us, one's going back into the page. And we're deprotonating this proton over here, right? So there's a maybe we have HHH, methyl ketone. I'm going to draw so which one of those protons is acidic? Antiperiplanar. In order to deprotonate, the sigma bond, the CH sigma bond needs to align with the pi system. That's why it becomes acidic. As these electrons donate into the carbonyl, that leaves the proton hanging. This proton is easier to pick off because of those electrons are contributing into the molecular orbital with the carbonyl. So when we deprotonate, we require the CH bond to align with the pi system of the carbonyl. Okay, so that's why the alpha position becomes acidic. And now we can take this and apply this type of an understanding to the deprotonation of these difluorinated carbonyls. And specifically, this is what I just mentioned. You need the alignment of the CH bond with the carbonyl to acidify the proton and facilitate deprotonation. Now, when you have that type of alignment in this type of a difluoromethyl ketone, we need the CH to be aligned here with the pi system, but when that happens, the fluorine atom would be close in space to the carbonyl. The dipoles, so the CF bond and the carbonyl, would be aligning, and that's disfavored. Instead, because of electrostatic repulsion, these types of difluorinated carbonyls would typically exist in a different conformation, one in which the CH would be closer to the carbonyl. The CF bonds would rotate so they're away from the oxygen atom. And in this situation, this proton is no longer acidic. You don't deprotonate that position. We'll see if we can deprotonate something over here on that side. And so this is a different projection. This is your Newman projection here. Again, you can see this is the alignment that you would need to deprotonate, and that has the oxygen and the fluorine atoms close to each other, and there's electrostatic repulsion. Instead, it prefers to sit in an orientation that would look more like this, and with computational error, there might be a little bit of a difference from what I drew here, but it would tend to have the hydrogen closer to the fluorine atom. Okay, cool. Okay, so let's come down to, how do you do this? How do you make these fluorinated enolates? From a synthetic perspective, there are other strategies to make these that do not rely on deprotonation. So here's one example. You might take like a difluorobromo ketone precursor, throw in a reducing metal, like zinc metal, get to a zinc enolate, and then you can work with that magnesium metal. You can get to a magnesium enolate. Okay, so that's, there's supposed to be one here. So that's one strategy. Just start with a bromo or an iodo or something else here. Another one might be a retroclason. So we can take a precursor like this and with an additive, deprotonate. If you deprotonate, electrons go down and we break the CC bond in a retroclason reaction. And that would also generate the enolate. Okay, so there are other strategies, other creative ways to get to these types of enolates that you can then use in chemistry, but you don't do it by deprotonation typically. Okay, cool. Is it a good way to end the morning session? And now we can go get our tea? Is it time? Okay. Thanks. 10:15 on the dot. All right. We'll come back to another question in just a little bit, all right?